Hello and welcome to another online lecture in Earth Science. This is Chapter 7, Crustal Deformation and Mountain Building. So rocks deform, or rocks change shape. We see that in a lot of deformed rocks we find on the Earth's surface. And what deformation is, it's a term that refers to a shift or change in position of a rock body. You can see it in the GIF there below, where there are some originally horizontally deposited rocks like here, and then with a little bit of compression they start to fold. All right, most of this deformation occurs near plate boundaries, okay, and that's specifically a response to stress being applied to these rocks. And plate boundaries, you know that there's convergent, divergent, and transform plate boundaries, and this is where the majority of the action occurs. And then as a result of this, there are a lot of geologic structures that result from these forces. We call them folds, faults, and joints, and it also creates foliation, which you should remember as a metamorphic rock texture, and rock cleavage. So here's some examples of folded rocks. Here we can see almost like this S-shaped pattern. We call this ductile deformation. Then over here, a fault will form, and that's called brittle deformation. All right, and here's another GIF showing you how once horizontal rocks can be kind of bent inward through compressive forces. So stress is that force that deforms these once horizontal rocks. And when stress is kind of impinging on a rock and it exceeds its strength, the rock will deform. And it'll deform by any of these four F words: flowing, folding, fracturing, or faulting. So the magnitude of the deformation is a function of the amount of force applied to a given area of the rock. If the forces being applied to the rock are equal in all directions, we call that confining pressure. And if they're unequal, meaning that the forces are kind of coming at the rock in different directions, we call that differential stress. And there's three types. There's compressional, tensional, and shear. So here are the different types. This is confining pressure. This is analogous to jumping into a pool and swimming to the bottom of the pool. You know, you have to kind of yawn or pinch your nose shut and blow to equalize that pressure. That's because you're under increased pressure. The weight of the water column is applying forces to your body equal in all directions. Okay. Compressional stress, which is pictured here, this is where a rock is squeezed. And so imagine this used to be a cube, like you see up here. It's the direction of the rock is shortened in this direction and elongated in this one. Okay. Tensional stress does the opposite. Tensional is pulling apart. That's the stress. Okay. So you actually lengthen the rock in this direction and shorten it in this direction. And then shear stress, this is where you have stress forces being pushed into opposite directions. And the best way to visualize this right here is imagine a deck of cards. You put your hand on the top of the deck and you push the deck this way. The cards down here won't move, and then the cards up here will move in that direction and create this unusual shape. Okay, and that's shear stress. In fact, here's a picture. You can visualize it kind of nicely right here. So strain is a measure of how much the rock body has kind of moved. Okay, so a change in shape that's caused by stress. So you can measure strain, like especially if you have a sedimentary rock with a fossil in it, that's a trilobite. They don't look like this. This has been stretched and kind of pulled apart because of shear stress. And you can measure how much a rock's been shortened or lengthened as a result of stress. Okay, so there are three types of deformation. Elastic deformation is when the rock returns to its original size and shape. Imagine a rubber band. So like start expanding that rubber band out bigger and bigger and then letting it go, the rubber band will return to its original shape and size after the stress is removed, right? But if you continually pull that rubber band out really far and far, it'll eventually snap, right? And then turns into a weird rubber noodle. That's called brittle deformation. That is when a material kind of, once you exceed its elastic limit, so the rubber band's elastic limit, then the rubber band will brittly deform and it'll snap, kind of like this cool dude is snapping a pencil. There you go, New Zealand. That's brittle deformation. You're changing the shape of whatever it is you're putting stress on forever, okay, and breaking it in a kind of rigid fashion. But you can also exceed the elastic limit of a rock or any other substance, and it can bend, and we call that ductile deformation. And the example here is a paper clip kind of being bent into a new shape, like a pretzel or something. Okay. And so when stress is applied gradually, rocks initially deform elastically, but over time you can exceed the elastic limit, and then it kind of falls into the realm of either ductile or brittle deformation. So here's an example of a rock that was ductily deformed, because you don't see a break, you just see kind of like a fold in these layers here. So there are a number of factors that affect a rock's strength, and then that'll determine whether a rock will deform brittly or ductily. And one of the most important factors is temperature. Higher temperature, or an environment with really high temperature where the rocks are under high temperature, they tend to deform by ductile deformation. Whereas if you're in a low temperature environment, typically closer to the surface of the earth, rocks will brittly deform. Another variable in this is pressure. And confining pressure kind of squeezes rocks and makes the kind of small spaces in between them disappear. And that makes them stronger and harder to break. So these tend to undergo ductile deformation. And so that means that's usually deep in the ground within the crust. Rock type's also important. If you have crystalline, igneous, and some metamorphic rocks, they're typically composed of minerals that have strong chemical bonds, and they're kind of interwoven together. So they will generally experience brittle deformation, but it really depends on other factors like temperature and pressure. Sedimentary rocks and metamorphic rocks with zones of weakness or different types of foliation, they'll exhibit ductile deformation because they're weaker. And then the last factor is time. So if you apply stress and these forces gradually over a long period of time, that will result in ductile deformation. So how can, what environments would you typically see ductile or brittle deformation? What will occur, more often? Well, if you're in the upper 10 kilometers of the crust, most rocks will exhibit brittle behavior. So they'll start to kind of break or form faults. Okay. Some of that brittle behavior are joints. Joints are kind of cracks from rock being kind of stretched or pulled apart. A lot of times that's just being at the surface. Rocks form under tremendous pressure deep under the ground, and when you have uplift and erosion exposing these kind of deep rocks, they kind of expand outwards and they'll form these parallel joint cracks. Faults can also form. That's a type of brittle behavior, and these are just fractures in the rock where there's displacement. Okay, and then folds are when rocks ductily deform. Okay, that's when rocks bend without breaking, and that typically happens in high temperature and high pressure environments, which means that's deep underground. So here are the kind of 6 examples. Here are the different stresses. Here's compression, tension, and shear. And then in this row here, this is the examples of brittle deformation. And then down here are the examples of ductile deformation. So if you have compressive forces, okay, as if a rock was in a vise, if the rocks deform brittly, you'll form a reverse fault. If they deform ductily, you'll get folding. Okay, and so these rocks start to fold. If there's tensional stress or pulling apart, brittle behavior will create normal faults where this block kind of falls downwards and these two go up. Okay, in a ductile deformational scenario, you get stretching, so you get thinning of these rocks here. Then if you have shear stress, the brittle deformational example here is a strike-slip fault where two blocks move in the opposite direction. It creates a fault. And then here you'll have stretching. Okay, so let's talk about ductile deformation, some examples of this. So folds, most folds result from compressional stress. So that involves shortening the crust and thickening it. And then the rock layers typically bend around what we refer to as a hinge line, which is an imaginary axis that cuts right through the center of the fold. And hinge lines can be horizontal to the surface of the earth, or they can be inclined. And then the axial plane is this plane right here that goes right through the center of the fold. Okay, so that's the center of the fold. These are the two limbs on either side of the fold. And then this here, this line here would be the hinge line. Okay, and typically when this compressive action occurs, then you'll have erosion, and see here, these would be exposed or outcropped rocks. And you can see they kind of dip downwards into the earth. So there are two types of folds, anticlines and synclines. Anticlines are upfolded or arched sedimentary rocks. So that would be this right here. That would be an anticline. Okay. And what you notice about an anticline is after erosion has taken place, so let's imagine you kind of cut, an erosive layer here. These older rocks, because they're up-arched, they're pushed upwards, you'll find oldest rock near the center. I have another image that will show this a little better. And then typically together, these folds occur together. You'll have syncline folds. So these are these down-warped folds here. So this would be a syncline fold here. So you see how these rock layers are kind of bent downwards? And here, if you create that erosive surface, the youngest layers will be at the center. And you'll see that, I guess, in the next slide. Then, depending on the orientation, the anticline and syncline pairs can either be symmetrical or asymmetrical. Okay, and the hinge line can actually plunge within the earth. And we'll take a look at that. Let's go right to the image because it's so much easier showing you this. So here's an anticline and syncline pair. These are symmetrical folds. And then you see here, the oldest layers are down here, the oldest rock. So in an anticline, after some erosion, these older layers get exposed at the surface. So that's why you typically see at the center of an anticline, you see older rocks exposed at the surface. At a syncline, because it's down warping, younger rocks are preserved at the center of the fold. Okay, this is what they look like in cross section. Okay, and the way I like to remember this, anticline starts with A, and that's what the rock layers look like, up arched rocks like this, A for anticline. And then when you see this here, this is in the field, live in action. Here's a syncline, and you get that down folded fold like this. Okay. Now, not everything's easy and perfect. Sometimes these are symmetrical folds. Sometimes you can have asymmetrical folds, and with asymmetrical folds, the axial plane is tilted. It's not straight up and down. So what happens is one limb ends up being kind of longer than the other limb. Okay. And sometimes this is so, compression can be so great that the fold itself can overturn, and this is very confusing, and this is what it would look like in the field. So this rock unit, which is the youngest one, has overturned and kind of overturned underneath some older rock units over here. It's almost like a crashing wave. Do you see this? Kind of a wave approaching and then crashing over. Here would be the overturned limb, and then you see here, this axial plane kind of almost becomes horizontal. Okay, it's like tilted, and this limb is thrust over to the other limb. That would be an overturned limb. So it can get kind of confusing. Structural geologists have a difficult job. And then the the hinge line is not always like right on like parallel with the ground surface. Sometimes they can point downwards. So they can, this is called a plunging fold. So the hinge line plunges down into the earth. And so what you see here, this is a plunging anticline. Here's the example in Wyoming. And in fact, you can see a lot of this. If you go on like Google Earth, go to satellite images, go out to Western PA, and you'll see this pattern in the exposed mountains there in the Valley and Range province. But this is what you would see. This is what the outcrop rocks would look like with this kind of parabolic shape here. And then this older rock that's up-arched because it's a syncline is exposed here, but then it kind of just disappears into the ground. Okay, and that's because of that. This is an inclined anticline, so that the hinge line's pointing downwards, and so the deeper rocks just kind of disappear as the fold moves in, and that's why you get that kind of exposed parabolic outcrop of rock. It's really interesting. There are also similar other structures created by ductile deformation. Domes and basins. Domes are upwarped circular features where the oldest rocks are in the center. And think of like the bowl you would have, where you'd have like a bowl of cereal. Now flip that bowl around, and that would be a dome type shape. And then basins, like how you would have a regular bowl of cereal, the bowl itself, not the cereal. And those are downwarped circular features. And the youngest rocks are typically at the center. So here's your dome. Okay, so you see that here are the upwarped circular features. And after erosion, you'll have exposed older rocks at the center. And as you travel outwards, you run into younger and younger rocks outcropped in circles surrounding it. And then here's your basin, and this is the octa. It's almost like someone put their finger in the center here and just pushed downwards, and then everything kind of buckled in a kind of concave upward fashion. And this is real. We see places here in the United States that show these structural features. If you've ever been to South Dakota to see Mount Rushmore, Mount Rushmore is a dome. So you see here, this is a cross-section from X to Y. So this is the cross-section of that area. And what you see here, see this? This is a limestone that's outcropped here, then it kind of disappears, but you see it on the other side. So at one point, they used to be connected over like this, and that creates that dome, but erosion has kind of since taken that over. And at the center of this dome is the exposed granite, right? And that's where they've carved those famous American icons onto the granite. Okay. Then if we go to the Michigan Peninsula, you can see here, this is a basin. And so here at the center of the Michigan Peninsula, you have the youngest rocks exposed here, and then in a circular fashion, older rocks outcropped further and further. You go away from this basin. Okay, so here's that underground kind of structure, the bowl, so to speak. And here's the upside down bowl. All right, then there's another structure that forms from ductile deformation, and it's called a monocline. And monoclines are step-like folds, okay? And typically occurs in horizontal sedimentary strata that kind of sits on top of more crystalline rocks. And so you see here, this is kind of horizontal sedimentary rocks, right? And then there's this kind of folded rocks right here. So it's almost like a one limb that's kind of folded downward like this, okay? So as basement rocks brittly deform, maybe create this fault, this pushes these once horizontal sedimentary rocks upwards, and then it creates that gentle fold that you see in a monocline. And a lot of times after there's some erosion, what you're left behind with is kind of this wall of kind of dipping sedimentary rocks. This is in Arizona. Here's the East Kaibab monocline. And a lot of these monoclines presented huge problems for people kind of settling out in the American West. It's hard to traverse. Okay, let's talk about brittle deformation now. And brittle deformation are when rocks kind of fracture and displacement has occurred. And we've kind of talked about this already. Along those faults, that's where earthquakes are created. And so the orientation of the fault is described by strike and dip. Okay, the strike is the direction of a horizontal line on the inclined surface. Okay, now I know it's going to be hard to draw, so just imagine this is three-dimensional. Oh God. Okay, that's not too bad. That's not too bad. Okay, so let's pretend the fault surface is here. Here's the fault, and then this is kind of two rock blocks here. This here is the fault surface, and then this here would be the strike. This is on the horizontal line. All right, so this is the strike here, S for strike, and then this is the fault surface. The dip would be this angle here, so that's the D. Okay, so the dip is the angle of inclination from the fault surface. So here's the fault surface, and it's inclined from this angle from the horizontal. I'm actually pretty impressed with that drawing. Okay, so let's show you some examples. Oh, we got GIFs. Dip slip faults occur when there's movement that's parallel to the inclination or the dip. And there's two features, a hanging wall and a footwall. The hanging wall is rock surface above the fault, and the footwall is below the fault. So here, this here is the footwall. We'll put an F here. Okay, the footwall, I like to imagine I'm a giant and put my foot here to tie my shoe. So this is the footwall block here, and this is H for the hanging wall block. Okay, and over here, this example, this is the footwall. Okay, and then this is the hanging wall. And I like to remember the hanging wall because, like, see that? You can kind of hang off of this sharp edge over here. I don't know. That's how I remember it. Anyways, so there's two types of dip slip faults because you can have motion in two ways. You can have normal, where the hanging wall moves down, and that's this example over here. You see that? H moves down, the hanging wall moves down. And then reverse, where the hanging wall moves up, and that's this over here. See, the H kind of moves up. That's the hanging wall that moves up. That's reverse, and this one's normal. N for normal. Okay. So let's take a look at this. Let's see if, can you guess what this is? All right, if this is the footwall, right, you can put your foot on it. Here's the fault plane. This is the strike of the fault. Here's the hanging wall block, right? What kind of fault is this? You said normal? Then you are correct. Yes, it's a normal fault. The hanging wall moves down. Okay, you can see these layers, how there's displacement. This pink layer used to be aligned with this pink layer, but because of the movement, they're no longer aligned. And when you go out into the real world, this is what you see. Look at that handsome fellow over there. So here are some, this is a rock unit, clearly the same rock unit over here, and they've been displaced. You can measure that displacement. And so here, what you have here, this is a footwall block, this is a hanging wall block. This is also a normal fault. Okay, normal faults are associated with tensional stress, where the stress is pulling apart. So the stresses are like that. And when you have this occur in a large scale on a tectonic plate, we call that fault block mountains. So you can create an area that has kind of mountain ranges as a result of tensional stress. And the best example of this here in the US is the Basin and Range province. And what you see is uplifted blocks, we call those horsts, and downdrop blocks, we call them grabens. All right, so here's your normal fault, N here, right? Your footwall moves up and your hanging wall moves down, and you get a normal fault. And then so what happens is because this footwall moves up, then and the hanging wall moves down, you're kind of exposing all these older rocks and creating a range over here. And then this is the Basin and Range province. So here you got range, basin, range, basin, range, basin, and it goes on forever. Like the entire state of Nevada is made up of these kind of north-south trending ranges and valleys. Okay, so we call this a graben here, this low-lying area that's filling up with sediment, and these would be the horsts. And that's the result of tensional stress or extension. Okay, reverse faults, they're associated with compressional stress. And these can create what we refer to as thrust faults. And a great example of this is at Glacier National Park, and these occur at convergent plate boundaries. All right, so here, hanging wall moves up, footwall moves down, F moves down, and then so this is a reverse fault. And so what happens, you also create mountains as well, because you're kind of pushing up older rocks upwards, and this is going downwards, and then over here you have some mountains. And here's some good example of the formation of a low angle thrust fault here. So all these rocks kind of were horizontal, but then they started compressing, right? Here's this direction of stress, and oh, I can't get the eraser. Okay, there we go. And then this fault forms right here, and then these older rocks are being thrust over these younger rocks, and essentially you can create a range like that. Okay, then there are strike-slip faults. These are characterized by kind of shearing type stress, where you have two blocks kind of sliding side by side one another. Okay, and there's two types. There's right lateral and then there's left lateral. And the way to figure this out is pretend you're standing on one of the blocks. Okay, so let's pretend we're on this block here, and you're looking in this direction. So you're facing this block over here. When you look at that block, which direction is it moving in? It'd be to your left, right? So therefore, this one right here is a left lateral strike slip fault. And the same is true as if you're pretending you're standing on this side of the block and looking over the fault at this block, and this block is moving to the left from your vantage point over here. So therefore, it's a left lateral strike slip fault. Over here on this example, if you're standing here and looking over the fault, this block is moving to the right, so this would be a right lateral strike slip fault. Here's another example. Here it is in the real world. This is the San Andreas fault. Can you tell me what type of fault this is? Right or left lateral? You are correct. Right lateral. Nice. Good job. So proud of you. Okay, so you can have large-scale strike-slip faults. We call those transform faults. They accommodate plate motion in very large plates. And one cool example is the Pacific Plate. Here's a simplified model of what's going on out west and why they have earthquakes. So this portion of California and Baja California here are part of the Pacific Plate, and they're kind of moving north westward relative to the North American Plate, and that's why there's all these earthquakes here. And here is the zone of all those transform faults. It really is like a zone of a lot of different faults, major faults that form here. There's another major one in New Zealand. That's why they have a lot of earthquakes there. And then there's one that goes through kind of like the Caribbean, part of the Caribbean plate, and goes right through Guatemala. Okay, joints are fractures in a rock where there's no movement, but so it's kind of like the rock is expanding and cracking in this parallel fashion. So these are all joint cracks right here. You see that? They mostly occur in groups, okay? And so when rocks are on the outermost crust, they'll experience this brittle failure. Okay. All right, let's shift gears and talk about mountain building. The fancy word for mountain building that geologists came up with is called orogenesis. And so the reason why they came up with this term is because a lot of things can happen in the process of creating mountains. So we kind of give it a blanket term called orogenesis. All the processes that collectively produce mountain belts is an orogenic event. And so most mountain building occurs at convergent plate boundaries, and you create compressional mountains. And that's what you're seeing here. This is a little model showing you how mountains are generated. So the first type of mountain building is associated with subduction. And remember, so a subduction zone is a convergent plate boundary. And here you have steady subduction of ocean lithosphere, right? Here's a downgoing ocean plate. Dewaters, creates melts in the astenospheric mantle. Those rise up, thicken the overriding crust here, and some of it erupts at the surface. to create kind of volcanic island arcs, right? And because of this kind of collision, this compression, the overriding plate kind of buckles and thickens as a result of it, and that's how you can kind of start the mountain building process here. And if this occurs over millions and millions of years, this leads to Andean-type mountain building. And this is where you have ocean and continental crust converging. So you see here, this is the subducting ocean lithosphere being kind of taken down, melts are generated. This kind of thickens and may erupt at the surface. A lot of them crystallize deep underground as intrusive igneous rocks, but as a result you have mountains like the Andes. God, I love how these little volcanoes smoke. So yeah, the Andes are kind of a majestic mountain chain that divide kind of Chile and Argentina, and they kind of go through Peru, Ecuador, and Colombia. Okay. And so what happens, the way this kind of onsets is you start off with a passive margin where there is no subduction, and then you get the onset of subduction and then continual subduction for millions of years, and that thickens this overriding plate and also pushes these rocks upwards and compresses them. Okay, so here's the example. These are the features that'll form. Here's the continental volcanic arc. You'll have a four-arc basin, a low-lying area where you'll have volcanic sediments deposit. The formation of an accretionary wedge. Here's a subducting plate. The reason why this is there, because a lot of times the ocean sediment can get kind of plastered on the continent here. A lot of intrusive igneous rocks, that leads to metamorphic rocks that are over here. And then back here is where you have the fold and thrust belt of mountains. Okay. So you have the continental volcanic arc form, that's this area, the accretionary wedge form, and then here are the Andes just west of the, east of the volcanic chain. Let's say the Andes as an example. Other inactive examples are the Sierra Nevadas in California, and California's coastal ranges were the result of Andean-type mountain building. Okay, so here's that process. You start off with a passive margin, right? There's no subduction here, as far away from plate boundaries, but then there's the onset of subduction, subducting ocean lithosphere. Here's the trench. This is the accretionary wedge starting to form, and then you're starting to create your continental volcanic arc. The crust is thickening. Those thrust faults start to form, and then you get a mountain chain like you see here. And this is basically what California essentially looks like. These are the Sierra Nevada mountains where Yosemite National Park is. Then there's the Central Valley in California, and then the coastal mountains here. This used to be a former accretionary wedge. Okay, then there's collisional mountain belts. And this is kind of more complex mountain building, and it's associated with Pacific-like ocean basins that are kind of like closing essentially, and island arcs or microcontinents collide with larger continental crust. And so this process creates like accretion of those small crustal fragments that used to be maybe island arcs or ocean plateaus or microcontinents, and that stuff gets plastered onto the continent. And we call those terrains or exotic terrains because they didn't really like belong to the continental crust, and they were just kind of added to it. And you can see that in this GIF here over the course of let's see, 180 million years. Continued subduction here, and ocean provinces and microcontinents and island arcs were kind of added to the western side of North America. And each one of these different colors represents different terrains that were added to the continent. This might make more sense here. So if you have a subducting ocean lithosphere, pretend this is the west coast of the United States. So here's the continental volcanic arc. And as you subduct this ocean plate, here is an inactive island arc. So think of like Japan or something, a couple of islands. This stuff is really buoyant and won't subduct with the downgoing ocean plate. So what will happen is it just kind of plasters itself and becomes part of the overriding plate. So you see that? You can see this kind of yellow color here. That's the material that just got added to it. So an island arc added to it. And then you can have something like a microcontinent, let's say like a Madagascar or something. that will approach the subduction zone, and it won't subduct. So it'll just get added piecemeal to the existing crust over here. And this happens repeatedly over and over again, and then what you get is a bunch of exotic terrains just kind of piled up on top of each other. And that's the case of the North American Cordillera. This goes from California all the way to the tip of Alaska. All these different colors that you see are different, either oceanic terrains or former microcontinents or island arcs that have been added to the West Coast tectonic plate. Okay, so that's why we refer to it as kind of Cordilleran-type mountain building. Very complex geology. If you go out here, it's complex because these are very old, deformed rocks. They've been through a lot. All right, and here is the distribution of modern-day oceanic plateaus. So these are areas that would be kind of accreted onto continental lithosphere if subduction kind of continues. And so basically these could be the new terrains or exotic terrains that could add on to continents. And the idea is that's how a lot of continental crust must have formed initially, is through this process of subduction. Okay, the last type of mountain building is called collisional mountain belts, or these huge continental collisions. We call these Alpine-type mountain building, where two continental crust like plates kind of collide. Okay, and the best example of this is the Alps or the Himalayan mountains. Here, this is the past 60 million years. India was kind of its own island continent, and it slammed into Eurasia. And as it did, it had a leading edge of a subducting plate, but it kind of ran out of that subducting plate. So initially there was a continental volcanic arc in Eurasia. You see that here. But then as the subducting plate kind of tapered off, then it was continental crust on continental crust, and that's what is pushing up all of those crustal rocks upwards and creating those majestic Himalayan mountains. That's a great GIF. Okay, so here's just another image of that. So initially, here's India. This was the subducting ocean lithosphere. You had a continental volcanic arc. All right, there were some kind of mountains here as a result of that continental arc volcanism. You could even say that this was kind of like a Andean-type mountain building before India just slammed into the Eurasian continent, and that's what formed what the Himalayas are today, the largest mountain chain and the highest mountain chain. Still growing. I mean, India is still kind of pushing northward into the Eurasian plate. And then there are the Appalachian Mountains. The Appalachian Mountains are much older, and they kind of record all kinds of crazy tectonic history. But if you go back 600 million years ago, here's the North American plate. There was a volcanic arc here in an ancient ocean before the Atlantic Ocean. Then there was a microcontinent over here, and then here was the African continent. So the first step that occurred was the tectonic orogeny. So here, this exotic terrain, this volcanic arc, was added to the North American tectonic plate. Okay. Then over the course of the next 100 million years, Avalonia, which was its own microcontinent, then slammed into the North American continent, and that added another exotic terrain to the North American continent. And then this is the ancestral Atlantic. It's called the Iapetus Ocean. And then Africa came in and then slammed into North America. And this was the kind of culmination and the building of the Appalachian Mountains in its totality. Okay, and at this time, about 250 to 300 million years ago, the Appalachian Mountains rivaled the Himalayas of today. Okay. Since this time, it's been 300 million years of slow erosion, and it's kind of rounded off a lot of the exposed rocks here. But yeah, this was in the time of Pangaea as well. So the dinosaurs were around this long ago, and this was a major mountain chain. So since then, Pangaea broke apart. Africa and there was a continental rift, and the rift kind of formed over on the kind of African continental side. And so actually a piece or remnant of Africa is still attached to the North American plate. And guess where that remnant is? Yeah, Florida. Florida, if you dig deep enough past the like 10,000 feet of limestone, you get down to African metamorphic basement. Isn't that incredible? So we were once part of Africa, and we ripped off of that lithosphere back when Pangea broke apart, and now a remnant of it is part of the coastal plain in the United States. And then these are the different physiographic regions: the Blue Ridge Mountains, Piedmont, and then the Valley and Ridge Province behind the Blue Ridge Mountains. So that's the story of the Appalachian Mountains. Okay, so let's talk about the principle of isostasy and buoyancy. Okay, there is evidence that there is crustal uplift, meaning like the crust rises upward above sea level because of features that the ocean will create. Like the ocean will erode continental margins and create wave-cut platforms that are very flat. But in a lot of areas, we can see multiple wave-cut platforms above sea level. So there's evidence that in certain areas, maybe because of plate tectonics, there's crustal uplift. But there's also another example of where crust can be uplifted, and that's the process of isostasy. And in this example, this GIF, it's going too fast, but this is an example of glacial isostasy. So when Earth is much colder during their ice ages, they'll have a lot of continental glaciers on land. And glaciers are very heavy. They can be kilometers thick of ice weighing down on the crust. And when it weighs down on the crust, it kind of pushes it downwards. And it makes the mantle flow move away, right, as that happens. And then what happens is you get uplift in certain areas, and then you get subsidence here. But when when climate changes and we're in an interglacial period, these glaciers melt away, and as they melt away, the weight of all that stuff is removed from the crust, and the crust actually kind of rebounds and rises. And that's true in places like Norway. Like right now, sea level is rising millimeters every year, really slowly. So globally, continental margins are seeing sea level rise. Okay, but in Norway, they're actually seeing local sea level fall, because the rate of crustal uplift is faster than the rate of sea level rise. So they're seeing sea level fall in their perspective, and that's just because the crust is rising faster. And so the way to understand isostasy is just to imagine floating crust that's in gravitational balance. And then when you have subsidence or uplifting, that's an isostatic adjustment. Okay, the book uses an example of floating blocks. I prefer, imagine, you ever see those container ships that carry those like 40-foot containers that go into ports, right? Just imagine this, right? Imagine one that's fully loaded. And as you remove those containers one by one and you empty one of those boats, what's that boat going to do in the water, right? It's going to rise, right? It's going to rise up as you remove that cargo. And likewise, if you put cargo back onto the boat's going to sink into the water because it becomes heavier. The same thing occurs with the crust, okay? And the same thing occurs when you have mountain building events. When you have mountain building events, you're piling up a lot of rocks. You're shortening rocks that were once kind of spread out into like an area like this. So basically, you're loading that container ship with all kinds of weight here. And so what that does is that changes the mantle flow, and it pushes mantle rocks away. I don't know if you've heard this, but icebergs, I don't know if you've heard that thing where icebergs are like or something like 20% of it is exposed above sea level and 80% of it is below. Well, with mountains, the ratio is like 1 to 6. So if you have a mile of mountainous rock piled up on top of each other, there's about 6 miles below it pushing downwards. Okay, so really this area of the continental lithosphere is loaded with a lot of rocks kind of all pushed together because of that compression. But over time, as mountain building ceases, erosion removes all of these rocks over time, over geologic time. It kind of removes the weight from this mountainous area. And as a result, the crust rebounds and starts to rise. So we call this isostatic uplift. So imagine that container ship having the cargo being removed. That means the boat will rise as a result of it. And that's what happens to the crust. The direction of mantle flow changes, and you get uplifting of the crust to its former position before mountain building ever occurred. Thank you.